how much space you occupy. But it is an odd thing. So let's just explore volume for a bit. And I'm going to need a volunteer for this. Okay. Yes. Would like to volunteer there? Yes. Yes. Hello. What's your name? Annie. Okay. Annie. Now, do you want to come around here, Annie? Now, here we go. This looks like some weird game, doesn't it? It sort of is, in a way. I hope you're up for this. Now, we've got one sphere here which is empty, and it's twice as big as these small spheres which are full of water, coloured water, right? Now, when I said it's twice as big, you didn't stop me there, did you? But you probably wanted to say, tell me more. What do you mean by bigger? Right? Good thinking. So I'll answer that question. It's an excellent question. So I'm talking about the width, so the diameter, right? So let me just prove that to you. This is 7.5 in width, diameter, and this is 15. Right? So across there, it's double. Now, the question to you, and this is really difficult because you're under the cameras, the lights and everything. I'm going to ask you how many of these, if we had to pour into that one, which is twice the diameter, would we have to pour in order to fill this up to the top? I.e., what's the ratio of the volumes? Now, I'm going to give you 2 seconds to think about this. God, you've already... And I'm going to ask the audience to think about this too, but not to shout it out, but to do the calculation in your heads. Because you all know the formula for a volume of a sphere, don't you? Right? 4 over 3 pi r cubed. All right, so you guys do the calculation, right? And we'll do the experiment. So go on then. How many do you think?
8.
8? Are you sure?
Yes.
Oh ho ho! Do you think she's right? Who thinks that is way too many? Quite a lot of you. And who thinks it's too few? And actually, it's a trick that we've only put 9 here. Some of you. Nice. Would we do that? Maybe we would. All right, so let's go. Why don't you have a go? You think 8. That's 1. Although this isn't going up very fast. That's 2. All right, that's 3. 4. Well, it's looking good for you, isn't it? Oh, that's 5. Are you getting nervous? A little bit. All right, that's 6. This is 7. And here we go. Oh, now the question is it going to be 8? And are you going to be victorious? And if you are you going to run up the stairs shouting a yippee? Yes! Fantastic. Well done. You. Okay, look. Thank you very much for that. And yeah, do have a seat again. Okay. So it's quite surprising, don't you think? You increase something by twice, right? The width, or the diameter twice, and your volume increases by 8 times. Now, Crash Test Dog is back, and he's bandaged up. He survived. Yes, that's like, I mean, the show must go on, doesn't it? How are you feeling? Oh, yeah, not too talkative. Fair enough. Okay, so how does this all relate to Crash Test Dog and Crash Test Hamster? Well, they're different sizes. So how different in sizes are they? Well, Crash Test Hamster is about 5 and a bit, and Crash Test Dog is about 25 and a bit. So Crash Test Dog is 5 times bigger than Crash Test Hamster. If you do the maths in your head, you're doing it up there now, that turns out that Crash Test Dog is 100 times bigger volume than Crash Test Hamster. 100 times. Okay, so that would mean, if that's true, that would mean that Crash Test Dog is 100 times heavier than Crash Test Hamster, right? Force of gravity on it is going to be 100 times heavier. So do you guys believe me on that one? Do you think that's at all believable? Yeah. 100 times heavier? Well, I've got some scales here, and let's just have a look at that, because let's measure it. So Crash Test Hamster, right, is about 100 grams. And a Crash Test Dog, even injured with his bandage, so it's a bit unfair because he's got a bit more weight. But oh, yes, just over 10 kilos. So Crash Test Dog is about, in fact, slightly more than 100 times bigger than Crash Test Hamster. 100 times heavier. So does that answer our question why Crash Test Dog had such a hard time when he hit the floor? Because he was 100 times heavier, had 100 times more force, hurtling him down to the floor. Well, it's not the whole story, because when you hit the floor, you can basically spread your weight, right, and the force of impact over a large area. So the pressure on every part of you will be reduced. Okay? So It's not just how much force you hit the floor with, it's how much you can spread it out. So that's about area, isn't it? This kind of thing called area. And so we really want to know whether Crash Test Dog is 100 times bigger area, whether the outside of Crash Test Dog is 100 times bigger area than Crash Test Hamster, don't we? That's what we really want to know. So what we did earlier is we scanned in with a 3D scanner these two animals, right, Crash Test animals, and we worked out their areas, and we've got them here. Oh yes, look, surface area of Crash Test Hamster is 100, and surface area of Crash Test Dog is 2,800. So that's a bit concern-making now. Now we're starting to get worried for Crash Test Dog. Too late, I know what you're saying. But anyway, because the area over which it could spread that force has only gone up by essentially 28 times, but the weight has gone up by 100 times. And this tells you something really fundamental about making things bigger. It's that the area to volume ratio changes when you get bigger. So as you get bigger, it turns out that your area doesn't keep up with your volume. You get more inside and you get less and less outside proportionally. And that really means that when you hit the ground, you've got less area to spread that force over. So we have an action replay. I know you've all been waiting for this action replay of the rather unfortunate accident. So this is Crash Test Hamster coming down and spreads its weight over a large area and survives. So we knew it survived. So it was OK. Now if we go to Crash Test Dog, what happens is Crash Test Dog comes down, tries to spread. It's got 100 times more force, but it's only got 28 times more area, and basically the pressure on all its extremities couldn't cope, and it split. But luckily, we could rebuild him, and he seems to be on the mend. So there it is. So it turns out the reason, right, one of the reasons why it gets easier for you to survive a fall when you're smaller, because you've got a lot of area and not very much volume. So your surface area to volume ratio is very high. And there's something else that helps you too, right? Because we've kind of gone on the assumption that they've hit the floor at the same speed. But did they? I mean, things don't always fall at the same speed. And I want to just show you something about that here with this demo. I've got a snowflake, and I've got a snowball, right? Well, they're not really snowflakes, but they're, they represent them, right? Now, they're the same weight. They're exactly the same weight, but they won't fall, or well, let's see. Will they fall at the same speed? OK. No, they won't. So that's interesting because basically they have the same force on them, don't they? They have the same force pushing them down, pulling them down of gravity because they've got the same weight. But this one has more area, so it has more air resistance. So if you think about that with regards to small hamsters, not only when they hit the ground do they have more area to spread it over, right? When they're coming down, they slow down quicker because of their surface to volume ratio is really good. And we know this, right? Snow falls very gently, doesn't it? If you take the same volume of liquid and you make it into a drop of rain, it hits the floor quite hard, actually. It hits the top of my head very hard, I can tell you. That's the price you pay for being a little bit bald. But anyway, let's not go into that. Thanks for bringing that up. OK. So, all right, so we know the rules now. The rules of falling are that surface to volume ratio is king. You really need to know this. So if instead of hamster was jumping off the tallest building, if it was me, right, then I could manipulate the rules, maybe. So let's say I jump off the building, right? I'm falling through the air, right? And then I realize that I haven't got a big enough surface to volume ratio. Doesn't that always happen after you've jumped? So I think, Hamish, chuck me the umbrella. Thanks. Hamish chucks me on the umbrella. And now I've increased my area, right? And so I'm going to slow down. And I fall much slower. So I basically am cheating. I'm actually increasing my area artificially. And this, of course, is the essence of a parachute. So parachutes work because they change. You cheat. You change your surface to area ratio. You add a lot of area, and you don't really change your weight very much or volume very much. So that's really cool. So actually, when you're parachuting, what you're doing is becoming a hamster. Okay? Parachutists don't talk about it like that. it's much more of a gung-ho sport, but that's really what's happening. So, okay, it's not just actually that it helps you jump off buildings, your surface to volume ratio, and survive falls. It's really important in your whole life. How many of you are fed up with people saying to you, oh, God, you've grown, or how tall are you now? And you're like, oh, why are you obsessed with my height? You know, that kind of thing. And then people constantly measuring your height. And you're like, next time, I've got a good line for you guys. You say, look, don't worry about my height. It's my surface to volume ratio you should be worrying about, OK? When I was a kid, I used to go to the swimming pool with my brothers, who were all bigger than me. And I used to start shivering about 10 minutes in, freezing, cold, blue. I went blue with cold. And they were like totally fine, swimming around for hours. And I always used to think, oh my God, they're sort of stronger, tougher than me, aren't they? But actually, they just had a lower surface to volume ratio than me. So your area is what cools you as a person, right? So that you evaporate water off you. And it's your volume that gives you your warmth, you know, the blood and all those kind of things. So if you haven't got very much volume and you've got a lot of area, then you're going to cool down fast. And so you're going to shiver. So the bigger you get, the less cold you're going to get in swimming pools. And this is also true